In the next series of videos, we're going to look at variables that affect the behavior of gas particles, specifically these four: temperature, pressure, volume, and number of particles. Now, when we look at these specific variables, there are some laws that have been proven over and over again to stand the test of time. No one has proven Boyle's law to be incorrect. Boyle's law looks at the relationship between pressure and volume. It says that the volume of a gas at standard temperature and pressure is inversely proportionate to the pressure of the gas. Oh, brother. In other words, the volume of a gas is inversely proportionate to the pressure. You're going to see a lot of this inversely proportionate, or sometimes they'll use the word indirectly proportionate versus directly proportionate. It means this: if I increase the pressure, I will decrease the volume. Whoa, there we go. Hello. That's what it means to be inversely proportionate or indirectly proportionate. If one variable goes up, the other variable goes down. If I increase the pressure on a gas, I decrease the volume. And we're going to study this in the lab. We're going to do all kinds of examples so we can prove it in the lab. But visually, it kind of looks like this picture of these pistons over on the side. They're trying to show that the amount of weight placed on the gas, these are all little gas particles, the weights represent pressure. So by going from one weight to two weights, I'm increasing the pressure on those gas particles, and then I'm smushing the gases into a smaller volume, which is fine because we know that gas particles can take on the complete shape and volume of their container, which is now smaller. So this might be kind of like my initial volume. We might call this V1. And here is my final volume, V2, with the increased pressure. It makes total sense if you really think about and visualize the behavior of gas particles in your mind. They're bouncing all over the place, but if I squish them into a smaller space, yeah, the volume's going to go down. In the lab, we're going to use a syringe. No needles. It'll be hooked up to the computer. And as you apply pressure with your muscles, you can visually see the volume of the gas is smaller. The gas gets compressed into a smaller volume. Now, in the lab, this only works. This relationship between volume and pressure is only legit if you keep all other variables constant. So in the lab, if we're studying the relationship between pressure and volume, this is very important. Constants. Variables that must not be changed. Temperature and number of particles. And here's the four variables that we're going to study: pressure, volume, temperature, number of particles. And for a lot of these little gas laws, if I'm studying the relationship between two variables, how does one affect the other? Then the remaining two variables need to be held constant. This needs to be done at a constant temperature and a constant number of particles. This is a closed container. I mean, if I count the number of gas particles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's got to be the same number of particles. Let's say I have this piston or a syringe or something like that. Ooh, this happens in the lab all the time. Picture a syringe hooked up to the computer. And you apply pressure to like the little piston, the plunger on the syringe. You're pushing down on the gas. And on the computer, you're going to see a reading of the pressure inside the syringe. There's like a little pressure sensor we're going to use. Now, you feel it it in your muscles. You're applying pressure. And then you look on the computer and you're like, what's going on? Like, the pressure's not increasing on the computer screen. Well, if you don't have this syringe tightly fitted onto the pressure sensor, you don't have a closed container, and the number of particles are decreasing. The gas particles are escaping. I mean, if for whatever reason, let's say this piston didn't fit snugly into the container, and I apply all this pressure, but if there's like some kind of a little leak or a hole, all those particles can just escape. And now if I really try to study these relationships in the lab, I'm not going to get accurate data. I also need to keep the temperature constant. What if I apply pressure, which would make me think that the volume should go down, but I also jack up the temperature? And we know that temperature is a measure of average kinetic energy. So if I increase the temperature, I should be increasing the movement, the kinetic energy of the particles. I'm increasing the collisions. I might not really see the volume drop. So I could apply pressure, which would make me think the volume would decrease. But what if I increase the temperature? It's like they negate themselves. So now if I try to study this relationship in the lab, I'm not going to get accurate data. If I also try to study this relationship in the lab and graph my results, which is what we're going to do, we should create a graph that looks just like this, where at my highest pressures, I have my smallest volumes. At my lower pressures, I have my highest, somewhere in there, my highest volumes. It's an inversely proportional relationship, and the graph always looks similar to this. Now, the other thing we can do is quantify this relationship by using this little formula. P1 times V1 equals P2 times V2. Okay, so obviously it's pressure and volume. P1 V1, that stands for your initial pressure and your initial volume. P2 V2, those are your final conditions, your final pressure, your final volume. Anytime we multiply pressure times volume, we should always get a constant. If I have a high pressure, I'll have a small volume. I could multiply those and get this value. And I could have the same value if I maybe like reverse the variables. I could have a low pressure, which would give me a large volume. And if I multiply them, I could still get the same value. So we can set pressure times volume equal to itself at various sets of conditions. Quantitatively, it might look like this. Super easy. The calculations in this gas unit are so simple. I will give you the formulas. I'm going to give it to you. I mean, they're just plug and chug. And I mean, in the real world, you look that stuff up. I'm going to give you the variables. I'll give you the formulas. But you have to know when to use them. And the bummer with the gas unit is that there's actually kind of a lot of formulas. So you have to know when to use them and then which one to use. Look at the data that's given in the problem. A sample of oxygen gas occupies a volume of 250 milliliters at 740 kPa. That stands for kilopascal, which is a unit of pressure. What volume will the gas occupy at 800 kPa? Kilopascal. So I would suggest look at the units that are used in this data set. So for example, I have volume in milliliters, and then I have a pressure in kilopascal. Oh, okay. So in a nutshell, the pressure units that you might see, kPa for the kilopascal, you might see ATM for atmospheres. You might see this TORR, TOR, that stands for Torricelli, after the guy that developed the barometer. And you might also see millimeters of mercury, mmHg, which is how we would read a barometer. It's like a big column of mercury. Any of those units would represent a pressure variable. For volume, you'll probably see either milliliters or liters. We're going metric. So you look at your data, I see a volume unit and a pressure unit, and then I will give you this. I will give you P1 V1 equals P2 V2. You just have to recognize that, oh yeah, this is Boyle's law. I've got pressure data and volume data, boom. Now it's plug and chug. The initial pressure is the 740 kilopascal. And my initial volume is the 250 milliliters. Notice there's decimals in there. The decimals are in there to show that these are, I don't know, maybe exact measurements. And that I do have 3 sig figs in both. What is the volume at 800 kilopascal? 800 kPa is my P2, that's my new pressure. V2 is my variable. Oh my gosh, this is so easy. At what volume? So you just plug this in and solve for your volume. V2 equals, plug this in my calculator. Now for sig figs, I usually go with whatever the given data set has. So the original volume, the 250 with a decimal, that is 3 sig figs. So I'm going to leave this as 231. And it'd be the same unit. If the original volume was in milliliters, my final volume is milliliters. Now the other thing I like about these gas laws is that you can see if your answer is reasonable. The pressure increased. I went from 740 kilopascal to 800. If I increase the pressure, I should decrease the volume. So I'm looking for something less than 250. And I increased the pressure. I didn't go like crazy increase, 740 to 800. So I would expect the volume to be a little less than 250. So let's say this were a multiple choice question and your calculator dies. You could probably pick a reasonable answer. It's obviously not anything greater than 250. And it wouldn't be something like 100 milliliters. That would be too small. Done. So easy. A sample of carbon dioxide occupies a volume of 3.5 liters at 125 kilopascal of pressure. What pressure would the gas exert if the volume decreases to 2 liters? Plug and chug. P1 is my original pressure, 125 kilopascal. V1 is my original volume, 3.5 liters. At what pressure I'm solving for P2? Would I decrease the volume to 2 liters? 2 liters. I'm solving for P2. Isn't this nice? Plug and chug. Okay, so what am I doing here? The volume is decreasing, so I need to increase the pressure. So without even plugging this in my calculator, I'm looking for something greater than 125. Everything has 3 significant figures. I'm going to plug this in my calculator and say 219 kilopascal. This would work the same whether it were atmosphere torr. It could be any pressure unit, any volume unit. You do not need to convert. And the other thing that we should make note of is that I didn't do anything different in these 2 problems because the first one was oxygen gas and the second was carbon dioxide. Who cares? Gas particles all behave the same regardless of the identity of the gas. Now, we'll talk about things that are different. I mean, obviously, oxygen gas is not the same as carbon dioxide. There are some differences that we'll talk about later. But these gas laws will apply to any gas, regardless of its identity. So there you have it, Boyle's law, the inversely or indirectly proportional relationship between pressure and volume.